I'm Caroline Fernanda, and this is my submission for Assignment 1, Emerging Science. First, let's consider why it's important to include cutting-edge research in our teaching. It's important because it enables students to gain an understanding of how they might apply the knowledge they are developing in a future career. In other words, it gives chemistry a clear link to the real world. It also enables students to begin to assess the strengths and limitations associated with scientific research and develop employability skills, as set out in the VCE Chemistry Study Design. Who does the research? For this assignment, I looked at the work Robert Kerr carries out at the Institute for Frontier Materials, and I believe it's useful for students to see how he has progressed from VCE chemistry to a degree, PhD and postdoc work. Rob is looking at ways to improve the lithium-ion batteries used in devices such as mobiles, laptops and cars. This is so they can hold charge for longer, not contain flammable organic electrolytes, and cost less compared to traditional lithium-ion batteries. Let's start by looking at how a lithium-ion battery works using this diagram. During charging, lithium ions flow from the positive anode to the negative cathode through the organic electrolyte, and electrons flow in the opposite direction. During discharge, ions flow back from the cathode, and electrons flow in the opposite direction through the outer circuit, powering whatever device the battery is connected to. When all the ions have moved back, the battery is fully discharged. This is because lithium would rather exist as a metal at the cathode than as an ion at the anode. This is what drives the reactions at the electrodes, and can be described as the potential of the lithium ion at the anode being higher than the potential of the lithium metal at the cathode. So the lithium ion will move to be at a lower state of potential. This can be referred to as electrochemical potential. Rob's research looks at replacing traditional organic electrolytes with ionic liquids. An ionic liquid is a salt which is liquid below 100 degrees C, and in this case at room temperature. Ionic liquids are preferable over traditional electrolytes because they have the potential to hold charge for longer, are not flammable, and cost less. In an ionic liquid battery, the electrolyte used is an ionic liquid, and the battery functions in much the same way as a traditional lithium-ion battery, with lithium ions gaining electrons at the cathode, and lithium ions and electrons being released at the anode during discharge. Rob is looking at a variety of ionic liquids. First, he checks their suitability as an electrolyte by measuring the current produced at different voltages. He also varies the amount of lithium ions present. This is what it looks like in the lab. His results will look something like this, where current is the y-axis and voltage is the x-axis. Anything above the blue line represents oxidation, anything below the blue line represents reduction. Students can use oil rig to help remember this. As in oil, oxidation is loss of electrons, rig, reduction is gain of electrons. Once Rob identifies an ionic liquid as suitable, he builds a coin cell. He tests this by charging and discharging it around 100 times and records the voltage over time as he does so. This allows him to assess whether the battery can be fully recharged multiple times and how steadily it discharges. For instance, we wouldn't want a battery that discharges in just a few seconds. We would want it to discharge steadily over time. And who knows, one day your mobile phone might be powered by a battery developed in Rob's lab. The chemistry can be described on the macroscopic scale as lithium-ion batteries we experience in everyday life, with their limitations expressed as the moment of anxiety we feel at noticing a low battery icon. At the microscopic scale, we can consider how a battery converts chemical energy into electrical energy using diagram diagrammatic representations, such as this one we looked at earlier. At the submicroscopic level, we can consider the redox reactions that occur within batteries and represent these as equations. The key concepts covered link to many areas of the VCE chemistry study design, including considering the common properties of ionic compounds in terms of their formation and bonding, understanding the nature of evidence, what oxidizing and reducing agents are, what redox reactions are, that redox reactions involve electron transfer, the reactions in a cell can be represented using equations, both half and full redox reaction equations, that cells have common features, as well as an insight into scientific research methodologies. This is a list of the references used to prepare this presentation. Finally, I'd like to thank all the researchers at IFM who took the time to share their research with us. And a special thank you to Rob for taking the time to show us around the lab, explain his work in more detail, and answer my many questions.